Welcome to the third lecture of module 3 of Chemical Reaction Engineering 1. In this module we are discussing stoichiometry. Before going to this lecture, let us have brief recap on our previous lecture. In our previous lecture we have broadly covered these two topics. One is stoichiometry for constant volume flow system, and second topic we have covered the stoichiometry for variable volume batch system. In case of stoichiometry for constant volume flow system, we have seen that when V volumetric flow rate V is equal to V naught for a general reactions of A plus B by A B to C by A C plus D by A D. For this general reaction, we have seen how the concentration Ca is related with the conversion. That means Ca is equal to Fa naught by V naught into 1 minus x is the conversion. So, this is essentially Ca naught, that is the initial concentration, that is Ca naught into 1 minus x. Similarly, for component B, Cb is equal to Ca naught into theta b minus b by a into x and so on. In this case, this theta b is nothing but is f b by f a. For stoichiometry for variable volume batch system, we have obtained the relations between volume and the conversion. So, the volume for case of batch reactor is V is related with the conversion as V naught into P naught by P into 1 plus epsilon x into T by T naught. So, this is the general expression for variable volume batch system, where the volume is related with the conversion, and then we can relate with the concentration. Here, if we incorporate constant volume systems, we will essentially get the constant volume batch reactor equation. Now, in this lecture, we will consider stoichiometry for variable volume flow system, and the lecture outline would be stoichiometry for variable volume flow system, and then we will summarize the stoichiometry whatever discussed till today. So, let us start with stoichiometry in variable volume flow system. The expression for variable volume flow system would be similar to that of the variable volume batch systems. In a similar way, we can obtain the stoichiometry table. Some examples of variable volume flow systems are, you can see the cooking gas cylinder, as you can see, with fitted with a regulator. So, if you just open the regulator, the flow will start and the volume will change. So, it is the volume gradually decrease inside the reactor, inside this cylinder. Other examples for variable volume flow systems, like if we have fluidized bed at rest and then we pass, you can see the fluidized bed how it looks like at rest. Now, if we pass the reactant to pass through the bed through the distributor, so the bed will expand. So, essentially the volume of this will change. So, this is another examples of variable volume flow system. Now, what we want for this? We want the volumetric flow rate small v would be in terms of the function of conversion. The total concentration at any point in the reactor, we can write C T would be P T or P by Z R T, where P is the pressure and Z as defined earlier for the batch system, it is the compressibility factor, R is the universal gas constant and T is the temperature. So, the total concentration at any point in a reactor, we can write C T as P by Z R T. Now, the same concentration at the reactor entrance, what would be the equation? At reactor entrance, we can write C T naught, that means at T is equal to 0. So, the pressure of the system we can consider P naught divided by Z naught, R and T naught. T is the naught is the initial temperature and Z naught is the initial compressibility factor at the reactor entrance and R is the universal gas constant. Now, we know for any flow system the concentration C T can be related with the molar flow rate by the volumetric flow rate. So, C T can be written as F T by V. So, from here we can write F T would be equal to C T V. Now, for C T naught we can write F T naught by V naught. V naught is the concentration at the volumetric flow rate at the reactor entrance, and from here we can write F T naught would be equal to C T naught into V naught. Now, this we know. Now, if we just write F T from here would be C T naught into V. So, C T naught as we set at the entrance conditions at the total concentration at any point in the reactor C T naught C T. So, this will be P by Z R T. So, if we substitute C T in place of here, so this F T we can write P by Z R T into V. Similarly, for F T naught we can write C T naught into V naught, and C T naught we know from here. So, we can substitute this over here and we will get F T naught would be equal to P naught by Z naught R T naught into V naught. Now, if we divide these two relations, this one and this one, and we would obtain these relations. So, basically we divide P naught P by Z R T into V is equal to F T divided by P naught by Z naught R T into V naught divided. So, this F T divided by F T naught. So, if we rearrange this, we would obtain V would be V naught F T naught by F T by F T naught into P naught by P into T by T naught, and that into Z naught by Z. So, if we consider Z, the compressibility factor Z would not change much at the reactor entrance and at any point in the reactor. So, this we can take as 1. So, in that case we would obtain this relation. Now, we have this relation and we know F T is related with the stoichiometry of the reactions as F T naught plus F A naught delta into X. So, if we substitute F T in this relation, we would obtain V would be V naught F T naught plus F A naught delta X divided by F T naught into P naught by P into T by T naught. So, this we would obtain. Now, if we just rearrange this relation, we can write as V is equal to V naught 1 plus F A naught delta X by F T naught into P naught by P into T by T naught. Earlier we have discussed that F A naught by F T naught is Y A naught. So, we can write V is equal to V naught 1 plus Y A naught delta X into P naught by P into T by T naught. Now, as from the definition of the epsilon, we have obtained that this is equal to Y A naught delta. So, if we substitute these two over here, so we will obtain V is equal to V naught into 1 plus epsilon x into P naught by P into T by T naught. So, finally, this is the relation which we will get with the conversion and extent of reaction with the volumetric flow rate. Now, our target is to express the concentration in terms of the function of x. So, we got the relations between the volumetric flow rate and the conversion. Now, our target is to express concentration in terms of the conversion. So, concentration of any species J for a flow system in terms of the conversion, we can write C j is equal to F j by V, which is equal to F j by V naught into F t by F t naught into P by P naught into T by T naught. Since C t naught is F t naught by V naught, so we can substitute over here C j would be equal to C t naught from here, F t naught by V naught would be C t naught into F j by F t into P by P naught into T naught by T. So, here this expression of concentration is for any component J. Now, if we write for component A, this relation would be C A would be equal to F A by V, which is from here would be equal to C t naught F A by F t into P by P naught into T naught by T. So, this is equations of Ca. Similarly, we can write for component B, we can write Cb would be equal to Ct naught Fb by Ft into P by P naught into T naught by T. So, we have relation of Cb as well. Now, V is equal to V naught into 1 plus epsilon x P naught by P into T by T naught. This we have derived this relation. Now, for any component j, we have this relation Cj is Fj by V. If we substitute this relation of V in this expression of in place of V, we would get Fj by V naught into 1 plus epsilon x into P naught by P into T by T naught. Now, to simplify, it would be Fj by V naught into 1 plus epsilon x whole into P by P naught into T naught by T. So, this is the relation of Cj. Now, we can write for component A, which would be Fa naught into 1 minus x divided by V naught into 1 plus epsilon x into P by P naught into T naught by T, and if we simplify, Fa naught by Va naught would be Ca naught. So, which is Ca naught into 1 minus x divided by 1 plus epsilon x into P by P naught into T naught by T. So, now similarly for component B, we can write Cb would be Fb by V into Fa naught into theta b minus b by Ax divided by V naught into 1 plus epsilon x, and we have defined the theta earlier. So, Fa naught by V naught is Ca naught into theta b minus b by Ax divided by 1 plus epsilon x into P by P naught into T naught by T. So, this is the relations where we can relate concentration with the conversion. Now, from this we can develop the stoichiometric table for the flow system, which can be written as follows. Flow, and particularly for gas flow system, the stoichiometric table for the first 4 columns, that species, there no change of concentration, and then remaining those columns remain same as in the case of the constant volume flow system, and it will be similar to the variable volume flow system, but the conversion term between the concentration and the flow rate would be little different. So, which we will summarize in this stoichiometric table. So, we can write Ca would be equal to Fa by V, which is equal to Fa naught into 1 minus x divided by V. We can write this would be equal to Fa naught into 1 minus x divided by V naught into 1 plus epsilon x into T naught by T into P by P naught, and we can write from here is Ca naught into 1 minus x divided by 1 plus epsilon x into T naught by T into P by P naught. For Cb, we can write FB by V, which is equal to Fa naught into theta b minus B by Ax divided by V, which is equal to Fa naught into theta b minus B by Ax divided by V naught into 1 plus epsilon x into T naught by T into P by P naught, which is equal to Ca naught into theta b minus B by Ax divided by 1 plus epsilon x into T naught by T into P by P naught. For Cc, we can write Fc by V, which is equal to Fa naught into theta c plus C by A into x divided by V, which is equal to Fa naught theta c plus C by A x divided by 1 V naught into 1 plus epsilon x into T naught by T P by P naught, which is equal to Ca naught into theta c minus plus C by A x divided by 1 plus epsilon x into T naught by T into P by P naught. Similarly, for CD, Fd by V, which is equal to Fa naught into theta d plus d by Ax divided by V, which is equal to Fa naught into theta d plus d by Ax divided by V naught into 1 plus epsilon x into T naught by T into P by P naught. Similarly, we can write in terms of the concentration Ca naught into theta d plus d by Ax divided by 1 plus epsilon x T naught by T into P by P naught. And for inert, we can write Ci would be Fi by V, which is equal to Fa naught theta I by V, which we can write Fa naught theta I divided by V naught into 1 plus epsilon x into T naught by T into P by P naught. And similarly, it would be Ca naught into theta I divided by 1 plus epsilon x into T naught by T into P by P naught. So, this is the conversion of different concentration in terms of conversion and the extent of reaction. Now, let us take an example. Consider the same examples which we have covered in case of the constant volume batch reactor. So, consider and also the variable volume batch reactor. So, consider the following elementary reactions with equilibrium constant K is equal to 50 liter per mole and initial reactant concentration is Ca naught is equal to 0.5 mole per liter. So, this is the reactions A2 twice B reversible reactions and rate of reactions is given minus Ra is equal to Ka into Ca minus Cb square by K. Find the equilibrium conversion XCF for the flow reactor. So, we have to find out the conversion XCF for a flow reactor where A to twice B for this reaction. Now, we can develop the stoichiometry table like symbol A for component A, the initial concentration is Fa naught, the change is minus Fa naught x. So, the remaining Fa would be equal to Fa naught 1 minus x. Now, for component B, initial concentration of component B is 0 and its change would be plus Fa naught x by 2. So, Fb would be Fa naught x by 2. Now, Ft naught would be Fa naught initially and Ft would be Fa naught plus Fa naught x. So, if we sum off these two, we will get Ft would be Fa naught plus Fa naught x. Now, the system is isothermal, T is equal to T naught and the isobaric system, that is P is equal to P naught. So, in this case V would be equal to V naught into 1 plus epsilon x and Ca would be Fa naught 1 minus x divided by V naught 1 plus epsilon x. So, since this is isobaric and isothermal system, the ratio between the temperature and the pressure, they are unity, they are 1. So, that cancelled out. So, we will have Ca would be equal to Ca naught into 1 minus x divided by 1 plus epsilon x. We know the initial concentration which are given, epsilon also we can calculate. So, we will get the relations between concentration and conversion. Similarly, for component B we can write Fa naught into 2x divided by V naught into 1 plus epsilon x. So, if we substitute over here, we will get twice Ca naught into 1 minus x divided by 1 plus epsilon x. So, we obtained the relations for Ca and Cb in terms of the conversion from the stoichiometric table. Now, this is the red expression and if we substitute the Ca and Cb which we have developed in the relations earlier, we can write Ra would be equal to Ca into Ca naught into 1 minus Xf. Here Xf represents the conversion in flow systems. In batch system we have written X, in flow system we change to Xf. So, Xf is the conversion in the flow system. So, we can write Ca naught into 1 minus Xf divided by 1 plus epsilon Xf minus twice Ca naught Xf divided by 1 plus epsilon Xf into K whole square. So, pure component A, we will have Ya naught is equal to 1, Ca naught is equal to Y A naught P naught by R T naught, and C A naught would be P naught by R T naught. So, since Y A naught is equal to 1, so from here we can write C A naught would be equal to P naught by R T naught. Here Y A naught is 1, so we substitute here 1 in case of epsilon, and delta we can see 2 minus 1, 2 moles is forming from 1 mole. So, it would be 1 into 2 minus 1, so 1. So, epsilon is 1. So, in this case if we substitute that part, we would have k square into 1 minus xcf is equal to 4 C A naught xcf square divided by 1 plus epsilon xcf. xef is the equilibrium conversion. So, if we solve it, we will get this relation xcf square divided by 1 plus epsilon xcf into 1 minus xcf is equal to k square by 4 C A naught. So, now epsilon would be equal to Y A naught delta, so which is 1 we have calculated, and this is the equations which we have derived. Now, if we substitute the values here, k is 50 which is given, and initial concentration is 0.5. So, this is coming to be 1250. So, if we solve it, it would be xcf square would be equal to 1250 minus 1250 xcf square. Now, if we rearrange, we can get 1251 xcf square which is equal to 1250, and from here we can write xcf would be equal to plus minus root over 1250 divided by 1251. So, if we take the square root of this, it would be plus minus 0.9996. So, the equilibrium conversion in this case we can write xcf is equal to 0.9996. So, because the conversion cannot be the negative, so you will take the positive root, so which is 0.9996. Now, if we recall our earlier solutions for the batch reactor flow systems, in that case for the same example we obtained the equilibrium conversion as Xc is 0.963. So, you could see the conversion for this case is higher than the conversion compared to the batch reactor conversion. Now, let us summarize what we have discussed so far in the stoichiometry. So, we have considered general relations of component A and B, they react and they form products C and D with a stoichiometric coefficient A for component A, stoichiometric coefficient B for component B, and producing C of C stoichiometric coefficient C and D with stoichiometric coefficient D. That means, A moles of A reacts with B mole of B and producing C mole of C and D mole of D. And we have considered A is the limiting reactants. So, we have considered A plus B by A B to C by A C plus D by A D. So, this is the overall general reactions we have considered, and then we have considered liquid phase and gas phase, both the reactions occurred in the liquid phase and reaction occurred in the gas phase. Now, flow system and batch system we have considered. For flow system we can write Cb is equal to Fb by volumetric flow rate. For batch system we can write Cb is equal to Nb by V. So, capital V is the volume of the reactant. Now, in the gas phase batch reactor Cb is equal to Nb by V, and for flow reactor we have also it will be similar to the liquid phase, Cb is equal to Fb by V. Now, if there is no phase change in the system, suppose in the liquid phase there is no phase change, so V would be V naught, and in this case a volumetric flow rate would be V naught constant, and in this case batch reactor they does not change much, the volume does not change much. So, we can keep V is equal to V naught, the volume would remain as constant. So, we can write Cb would be equal to Ca naught into theta b minus b by a x. In case of gas phase, if the constant volume system V is equal to V naught, then we can write V is equal to V naught Nt by Nt naught P naught by P into T by T naught. This is for variable volume system. Similarly, for variable volume flow systems we can write V is equal to V naught Ft by Ft naught into P naught by P into T by T naught. Similarly, Cb we can write Nb by Nt into Nt naught by V naught into P by P naught into T naught by T, that is for batch reactor. In case of flow reactor we can write Cb would be equal to Fb by Ft into Ft naught by V naught into P by P naught into T naught by T. And so, we can write this, rearrange this relations, Cb would be Ct naught because Nt naught by V naught is Ct naught into Nb by Nt into P by P naught into T naught by T. Similarly, in case of the flow reactor we can write Cb would be equal to Ct naught Fb by Ft P by P naught into T naught by T. But if it is constant volume batch reactor V is equal to V naught, so in that case we will obtain this relation even if in the gas phase. Cb would be Ca naught theta b minus b by a into x. Now, if there is no phase change or no semi permeable membrane, in this case for gas phase both batch and the flow reactor we can write V is equal to V naught into 1 plus epsilon x into P naught by P into T by T naught, and Cb we can write Ca naught into theta b minus b by a x divided by 1 plus epsilon x into P by P naught into T naught by T. So, this is how we can obtain for the gas phase system where there is no phase change. If it is isothermal, then this will be 1. So, we will get Cb would be like this. If it is isobaric system, that is neglect pressure drop isobaric system, this would be 1. So, finally, we will get Cb would be Ca naught theta b minus b by a into x divided by 1 plus epsilon x, and delta we have epsilon we have obtained earlier, epsilon is equal to Ya naught into delta, and delta is the change in mole into the reacting systems, that is D by A plus C by A minus B by A minus 1, and Ct naught is equal to P naught by RT naught, and CAD is equal to Ca naught is Ya naught into Ct naught. So, this is the overall summary of the stoichiometry chapter which we have discussed in 3 lectures, and this would be the basis for solving the other reactor design part in other sections which we will cover in other modules. So, thank you very much for attending this lecture, and we will continue our discussion on the other modules in the next lecture.